Exactly. Well, you. Do you
All right. Hi, everyone. Let's get started. Welcome to the CFA Colloquium. Today we have Ilya Mandel here from University of Birmingham. Ilya did his PhD with Kip Thorne at Caltech about a decade ago. Then he did a couple of postdocs at Northwestern and MIT before moving to Birmingham as a lecturer, and now he's a professor there, and he'll be telling us today about all the latest in gravitational wave astronomy. So take it away, Ilya.
Thank you, and thank you very much for the introduction. And look, this even works. Fantastic. Although it's much nicer to have one of those, old-fashioned ruler pointers, because that way, when people fall asleep, you can just kind of bang it in front of them and they wake up. No, it's all right. It's all right. Maybe it's better for everybody's safety. Just getting late in the afternoon. Well, as you can guess, the topic is gravitational waves, and you know that you've kind of made it into popular culture when there are inside jokes about your field featured in the New Yorker. So this is an example of one of them, two birds sitting on a tree, and underneath it says, "Was it you I heard just now, or was it two black holes colliding?" So the assumption is that the typical reader of the New Yorker knows that when black holes merge, they go chirp. So anyway. So that means the field has matured a bit. Hopefully what I can tell you a little bit about, since I know that there have been many talks on the topic of LIGO discoveries and gravitational waves in general here over the past few months, is a little bit about what my group and I have been doing specifically in terms of trying to go beyond just having those detections, but trying to interpret them in order to explore binary evolution, astrophysics, and to test general relativity. So this is the chirp heard around the world. Sounds something like this. It's a very short chirp. Only takes up a small fraction of a second in the detector band. Of course, you see the two black holes spiraling into each other, merging, eventually quasi-normal ringing of the merger product, just a few oscillations in the end as the newly formed black hole tries to get rid of any excess hair and look like the nice curved black hole that we all know and love, which is described by just its mass and its spin. Of course, in the process, the two components are moving relative to each other with a velocity approaching something like half of the speed of light. And the ability to detect even these few cycles gives us a very good handle on trying to test strong field gravity, but also gives us an opportunity to learn something about the parameters of the black holes that are encoded in the signature, and therefore, eventually, with the population of these sources, to learn something about how these binaries are formed. And so that's what I will spend the rest of today talking about. Okay. I probably should have turned up the sound. That's a chirp. So here, because the other event was sort of a bit too short, I actually played a neutron star, a 1.4 solar mass neutron star falling into a 10 solar mass black hole. Now, of course, the picture is fundamentally the same. You still have gravitational waves being emitted, traveling outwards as ripples in space-time, traveling at the speed of light, carrying energy and angular momentum away from the binary. So the binary is shrinking ever faster. So you have an increase in frequency and an accompanying increase in amplitude, hence the chirp. And if you listen to a slightly different system, in this case a slightly more massive system, you will see that the basic features are the same, but the sound is a bit different. the frequency and the rate of the evolution of the frequency are different. They're a function of the mass. They're a function of the mass ratio. They, as it turns out, are also a function of the spins of the black holes. And so that means that you might have hope that not only can you detect these signals, but also from the signature, you can go back and figure out what are the source parameters. Okay, first, of course, you have to detect them. And I'm not going to tell you very much about detection, except to point out that, of course, LIGO has detected not just one event, the event I showed you in the very first slide, GW150914, but also one additional event, which, as you can see here, is standing out very strongly above the background. So basically, black is the background distribution. Orange are the foreground zero lag events on here. And the events that are far up and to the right of the background distribution are things which you don't expect to happen just because of detector noise, right? So these three orange squares over here are things which you don't expect to happen because of detector noise. This one is, of course, the loudest one, GW150914. But there is also a very confident detection, GW151226, and a slightly less confident candidate event, LVT151012. Really, it's a third detection, but the LIGO collaboration doesn't want to call it that, so I'll follow their lead and not officially refer to it as a third detection. But it has a well above 90% probability of being the real deal. Okay, so three observations look like this. This is the event GW150914 with the largest masses. Higher masses means that you have fewer cycles in band because the evolution is more rapid, and because the maximum frequency you reach is lower. Maximum frequency you reach just goes as 1 over the mass, because the mass has the time scale, and so frequency goes as 1 over the mass. Somewhere in the middle, LVT151012, and a longer, more than a second, very long signal for LIGO in this case. Of course, we were expecting binary neutron star signals that might have lasted minutes, but for binary black holes, this is sort of on the relatively long end, almost 2 seconds, is GW151226. Okay, sorry. So very good. So we've seen something like this. Of course, we haven't quite seen this. This is actually our best attempt at reconstructing the signal. You might ask the question, so what is actually hiding underneath? You have this noisy data. You want to learn what were the parameters of that signal. Now, how do you do that? Well, we have models. There are models that are predictions of general relativity. Certainly early on, during the Inspiral, you can do this perturbatively as a post-Newtonian approximation. The same thing, in fact, goes for the quasi-normal ringing at the end. In between, it used to be the there be dragons territory. As recently as about 11 years ago, nobody knew how to connect the post-Newtonian Inspiral to the perturbative ring down. Turns out that you connect them in the simplest possible way. You draw a nice smooth curve between them, and it turns out to be the right answer. Actually, probably could have been predicted. But to do it confidently required numerical relativity, the solution of Einstein's equations on a computer. And that was a very long and difficult challenge that after 30 or 40 years of work finally was resolved in 2005 by a number of people. Franz Pretorius was the first, but others followed shortly thereafter. And so now we have these very accurate waveforms as a function of the signal parameters. So now what you want to do is you want to solve the inverse problem. You want to take the data, compare it to a large set of possible templates that correspond to different signal parameters, and figure out which ones of them match best. And we do this in a Bayesian way, and we do this stochastically with for example, a Markov chain Monte Carlo, because we want to explore a very large dimensional parameter space of 15 or so parameters. So I'm not going to write any equations down, but instead we'll show one more movie, which sort of shows only in 2 dimensions, because I don't know how to make a 15-dimensional movie, how you gradually start putting down points given a particular data set in the mass space, the 2-component masses, and you gradually reconstruct the posterior probability density function on the signal parameters. So here's a plot. As you can see, initially there were just a few random dots over here, and then gradually over time, you're filling this in, and you see that there's this nice banana-shaped uncertainty region. There's actually physics to why it's banana-shaped. There's basically one particular mass combination that is perpendicular to the banana, which is the chirp mass, and that at lowest order determines the phasing or frequency evolution of the binary, and the parameter along the banana is the mass ratio, some variant of it, and that's unfortunately something you cannot determine as accurately because it only enters at a higher post-Newtonian order. But gradually we can recover the parameters of the signal, and having done that to all of the LIGO detections and confident candidates, here are the posteriors on the three objects of interest. Now I'm going to show this because I want to later on discuss how to interpret these observations, so we better remind ourselves what is it that LIGO has actually seen. And what LIGO has seen are three events, roughly speaking, a 30 plus 30 solar mass binary, which is GW150914, a 15 plus 15 solar mass binary, which is LVT151012, and a 10 plus 10 solar mass binary, which is GW151226. Now, of course, I say 10 plus 10, 15 plus 15, 30 plus 30. That's on this diagonal, the equal mass diagonal. Of course, there are big uncertainties about the actual mass ratio, right? These are the bananas that I showed you earlier. These are generic to LIGO data analysis, and the kind of degeneracies that are present in the LIGO data. It's not an issue of, can we have better techniques? This is fundamental to the way gravitational waves encode the source parameters. Of course, we don't know the exact mass ratio. In fact, it could be the mass ratio is as extreme as 4 to 1 or 5 to 1 for some of these lower signal-to-noise ratio events. Okay, we know the final masses, and actually, remarkably, the final spin is known reasonably well. Well, it's not so remarkable. It's actually because the final spin is largely dominated by the orbital angular momentum. And so if you have, for example, an equal mass non-spinning binary, the final spin is going to be 0.7 in dimensionless units. So that's why you see that these things are kind of around 0.7. The spin parameters are not measured very well, except for the fact that we know that none of these events are really consistent with having two very highly spinning black holes with spins aligned with the orbital angular momentum. So that doesn't seem to be the case. And also we know that for at least one of these events, namely GW151226, at least one of the black holes must have had some spin aligned with orbital angular momentum. So it cannot be the case that both black holes are completely non-spinning. But for example, the spins in the orbital plane are very poorly constrained. In principle, they could have a signature in terms of the binaries precession, but it's not evident here. And in terms of the distance, GW150914 and GW151226 are both at about a redshift of 0.1, around 500 megaparsecs. LVT151012 was about a factor of 2 further away with big error bars. Okay. So the first thing I wanted to mention, because actually my postdoc Walter Del Pozzo led this work for the LIGO and Virgo collaborations, is the opportunity to test general relativity with these observations. There are a few different ways you can test GR, but fundamentally they all boil down to null hypothesis tests, right? They all boil down to saying, look, do we see any evidence that would suggest that GR cannot correctly explain these signals? Now, keep in mind that absence of evidence is not the same as evidence of absence, right? So we're not saying that GR therefore must be the right theory of gravity. In fact, there are many alternatives which have parameters that can be sort of tuned arbitrarily close to GR, so it's extremely difficult to rule them out completely. But certainly at the moment, there is no evidence that would suggest that there are any flaws in GR as an explanation for these events. And I'll just mention a couple of these tests, although there are, you can imagine many other tests. But one of the possible tests is, let's take a look at the early part of the signal, right? The Inspiral, the sort of low frequency part. Let's take a look at the late part of the signal, the merge and ring down, the high frequency part. And let's separately estimate the signal parameters from the early part of the signal and the late part of the signal, and ask, do they match up? Are they consistent with each other, right? If they don't match up, if they don't overlap, okay, we know there's a problem. Well, they do overlap because here's, for example, the total mass and the final spin that you would have guessed from just the Inspiral part. Here it is if you only looked at the late merge and ring down. And of course, they overlap, and they overlap precisely in the region which you would predict if you use the full data set, which of course gives you much smaller uncertainty bounds. Okay. Another test you can do, given that a significant fraction of the signal does come from the Inspiral, and the Inspiral is described in terms of this post-Newtonian approximation, so a perturbative expansion in powers of v over c, the binary's orbital velocity over the speed of light. 0 pn here, because it's different than what a zero is different for different people. 0 pn is the lowest order at which you have energy loss to gravitational waves, right? So this is the first term at which you actually have gravitational waves themselves. For people who are used to doing things like orbital dynamics, it's actually a 2.5 pn term in their language. Of course, here the upper limit on any fractional deviation in the corresponding post-Newtonian coefficient away from general relativity is poor relative to the upper limit you can place from the double pulsar, because the double pulsar has a much, much longer baseline, many more cycles, which help you very much with the zeroth order term. But of course, for any higher order terms, the upper limits from the double pulsar, for terms beyond 1 pn don't even make it onto this plot. You're basically not in the strong field regime. Your V over C is order of 1 over 1,000 for the double pulsar, and so really this is the best available strong field test of general relativity, and so far it passes with flying colors. Okay, you can actually also look at the mass of the graviton by seeing whether or not there's any evidence of dispersion in the gravitational wave signal. The answer is, of course, there's no evidence of dispersion, so you can place an upper limit, which means that the graviton's effective Compton wavelength is more than 10 to the 13th kilometers. Or if you wish, its mass is less than about 10 to the minus 22 electron volts. Okay, so enough about testing GR. Let's talk a bit about astrophysics. So let's just, first of all, forget about the binary nature of things. Let's just think about the masses of these black holes, right? So there's no right and left here are completely arbitrary. It's just a nice picture made, I think, by Mark Favata. But here are the binaries we know from observations of black hole X-ray binaries. Here are the black hole masses, and they are sort of in the 5 to 15 or 20 solar mass range for reasonably confident dynamical mass measurements. Here's a paper by Will Farr. Ferial and collaborators have another paper that also has looked at black hole observations and has a nice catalog of black hole X-ray binaries. And I'm not going to discuss the mass gap question, but the basic point is that there are quite a few measurements of low mass X-ray binaries, but of course they typically have fairly low black hole masses of around 5 or 10 solar masses, and there are only a few halfway decent measurement of high mass X-ray binaries, and a couple of them I would actually cross out because probably we're seeing the winds and not the orbital velocity. So really there's sort of no particularly good evidence of any stellar mass black holes above 20 solar masses before the LIGO observation. So that's already exciting. LIGO has sort of seen the highest mass black holes around. Not only that, it has shown that they exist in binaries and that those binaries can merge within a Hubble time. So that's 3 observations for the price of 1. Okay, great. So LIGO has seen these things merging, maybe forming, or in fact, definitely forming these black holes of going up to 60 solar masses, but starting out with roughly 30 solar mass companions. And the first question you ask when you look at this is, okay, hold on. So, well, beyond the question of how does this match up with the fact that there haven't been any X-ray binaries with black holes in that mass range that have been convincingly discovered, can we even form black holes this massive, right? So there's this big question of the mass problem. How do you make black holes that have a mass of 30 solar masses apiece? Well, the answer is you have to somehow avoid having too much mass loss, right? If you start out with even a very massive progenitor, but you start out at solar metallicity, it's really difficult to get black hole masses that are much larger than, give or take 15 solar masses. You need to go to lower metallicity where you can significantly suppress the winds. If you suppress the winds, you don't have as much mass loss. You can end up with a more massive remnant. And indeed, if you go to sufficiently low metallicities, probably at least less than half or quarter solar, most likely less than about a tenth solar, you can get up to 30 solar mass black holes. Okay, second problem. You want these things not just to be this massive, you want them to merge. So now you've got a separation problem. What do I mean by separation problem? If you want two black holes to merge in a Hubble time just through the emission of gravitational waves, they actually have to be pretty close together. Because the time scale for the evolution of the binary due to gravitational wave emission goes like the binary's separation to the fourth power. Right? So if your binary is just a little bit wider, it takes a lot longer for it to merge. And for the typical masses we're talking about here, it basically means that your binary cannot be much wider than about 20 or 40 solar radii when your two black holes are initially sitting there, if you wanted to merge through gravitational wave emission within a Hubble time just on its own without help from anybody else. So that's what this plot shows. It basically shows the time scale, and sort of this tells you this is the time to merger, right? So each dot corresponds to an extra factor of 10 years. So here, a binary sitting over here with initial separation of about 10 to the minus 3 astronomical units would merge in only 10 years. But if you have zero eccentricity, it would it would take you from about 0.2 astronomical units, so about 40 solar radii. It would take you essentially a Hubble time to merge. Okay, problem is, how do you mesh that with the fact that massive stars expand as they evolve off the main sequence, right? So thanks to a couple of people in the audience here for their nice work on MIST, the interpolator for MESA stellar evolution codes. Here is what happens to stars, the maximum extent that stars reach at, in this case, 0.1 solar metallicity, just as an example, as a function of their zero-age main sequence mass, and in red is sort of the maximal radius in units of solar radius that the stars reach on the main sequence. This is what happens during, essentially, let's call it the Hertzsprung gap. And finally, this is what happens in terms of the maximal extent when the star is a giant. And you can see that stars are getting to be at least, massive stars are getting to be at least 100, more like 1,000 solar radii, and that's at 0.1 solar metallicity, even a bit larger at solar metallicity, right? So you've got a problem. The problem is you need your two black holes to be this close together, but somewhere in the process of making these two black holes, the two stars that are going to make them are this big. So how do you reconcile those two, right? How do you get your two black holes to be this close together without the stars having merged when they were this big and the black holes were only this far, their progenitors were only this far apart? So that's one of the big challenges. And, well, there are probably three solutions that at least 3 solutions that come to mind. One is somehow when the stars are this big, the binary also has to be this far apart. And the binary only comes close together once the stars get smaller, after the stars have evolved. Okay, that's option 1. Option 2, you've got to somehow kill this picture and not let the stars expand. When the stars are on the main sequence, right, they're only about 10, 20 solar radii, right? That's still enough for them to fit within this picture of leaving you a binary that's no more than 40 solar radii apart. So somehow you just don't let the stars expand. And then the third option is, well, what if your 2 stars didn't actually end up starting their life in the same binary? What if they come from different binaries or they evolve independently and then somehow only after they've made black holes do they end up in the same binary? Okay, then you don't have this problem. Now, okay, there are a couple of other alternatives, of course. I mean, one of the things is that notice everywhere in here I talk about stars. So, of course, you can have maybe 2 black holes coming from the same single star, right? So this is Avi's proposal. I won't discuss it today. Or, as we heard during the lunch talk today, maybe these things don't come from stars at all. Maybe they come from primordial black holes. So, again, won't discuss that. I'll talk only about 2 stars and a binary that, at least in some way, represents the evolutionary end products of 2 stars. Okay, so let's try to discuss these 3 approaches one after the other. So first is, how do you harden the binary after the stars have evolved? So this is, in some ways, perhaps the oldest of the prescriptions, because these discussions started in the 1970s. And the idea is that this is sort of the classical isolated binary evolution via what's called a common envelope phase. And yes, there are far too many references here, so I'm sure that there are many that I've missed as well. This is a very rich field with a long history. But I'm going to show you, taking advantage of the fact that I'm the one speaking here, not any of the people who were involved in the very rich history. I'm going to actually show you a plot, just as by way of illustration, from a work that my students are doing at the moment with our compass code that I'll mention a little bit later. So this is work led by Simon Stevenson, a final year student at Birmingham now. So here's a picture of what might happen to these 2 stars, right? So this is how you may have formed an event like GW 150914. And this, by the way, here is happening at 5% of solar metallicity. So you start out with 2 quite massive stars, almost 100 solar masses, 75 solar masses for the secondary, about 2,000 solar radii apart, so definitely safe, plenty of space for them to evolve. Nonetheless, as the stars are evolving, of course, at some point the primary evolves off of the main sequence after about 3 million years, starts to expand, and begins to overflow its Roche lobe. So it's being now tidally distorted by the presence of the companion, and it's beginning to transfer mass over to the companion. There's a fair bit of mass transfer. The mass transfer in this case we think is mostly non-conservative. So most of the mass is actually ejected from the binary. As a result, the binary ends up being widened, so it's now 4,000 solar radii at the end of this process. And the primary makes after a supernova at 34 solar mass black hole. Then the secondary begins to expand, and as the secondary expands, at some point it starts to transfer mass back onto the primary, because now it's the secondary that's expanding and overflowing its Roche lobe. But now this mass transfer is dynamically unstable. So as the mass is taken off the secondary actually wants to expand even more in response to the mass loss. As it expands more, it overflows its Roche lobe by an even greater amount. The mass transfer speeds up further. So we have this runaway process, and in the meantime, our primary, which is now a black hole, it just can't accept all of this mass, right? I mean, if you think about, for example, the Eddington limit, right? It's only able to accept a tiny amount of mass, right, at a very low rate. So all this mass transfer that's happening here, this mass is not sticking to the primary, it actually ends up expanding well beyond the Roche lobe of either the primary or the secondary, and ends up forming a common envelope around the binary system. Now you've got these two stars, or a black hole and a star, a core of a star, that are swishing around inside a fairly dense cloud. Of course, there is friction against the cloud. There is energy dissipation, so the cloud is getting heated up. Ultimately, at least in some cases, and this is one of the big uncertainties here, exactly when does this happen, what are the necessary conditions for this to happen, but at least in some cases, this common envelope is ejected from the system. Enough energy from the orbit of the binary is pumped into the common envelope that you drive the common envelope out of the system. It takes away a significant fraction of the orbital energy, and as a result, the binary now shrinks, because so much of the orbital energy went into expelling this common envelope. And it actually shrinks by many orders of magnitude. So here, this system shrinks by about 3 orders of magnitude, from more than 4,000 solar radii to only about 30 solar radii. Okay, then it expands a little bit more because we've got this naked helium star here, basically a Wolf-Rayet star, which of course is losing quite a bit of mass through winds, and mass loss as usual is driving the binary a bit further apart, but ultimately it collapses into a black hole, and when the binary is still a bit less than 40 solar radii apart, which as I said is roughly the magic number for systems like this, and so it just about manages to merge in a Hubble time, right? So that's the classical picture of isolated binary evolution with a common envelope. That's how you might form binary black holes. Okay. Alternative picture. Well, what if we don't let the stars expand? How can you prevent the stars from expanding? Well, it seems a bit counterintuitive. We know that stars should expand, but maybe there's a caveat. And this caveat is chemically homogeneous evolution. What if you somehow manage to avoid the situation where you have, at the end of the main sequence, you've got this nice helium core in the center because all of the hydrogen burning was taking place in the center of the star, and you've got this shell of hydrogen around it, this envelope of hydrogen, and the helium core contracts once you've stopped burning hydrogen. As a result, there is energy release, the envelope expands, and now you have an expanding star. How do you avoid it? Well, one way to avoid it is if you somehow don't have this picture of just having this helium core in the center and a bunch of unused hydrogen on the outside. What if somehow you manage to mix up the whole star so that you actually burn through essentially all of the material in the star? You only have, almost exclusively have helium left at the end of main sequence burning, then the whole thing just contracts. Never expands at all. The star doesn't become big and red. At the end of the main sequence, it becomes small and blue. So can you do that? Well, we argued actually a bit earlier this year with Selma Deming that yes, you can. And there's been a very nice paper that attacked this in a somewhat different way by Pablo Marchand and collaborators. So let me discuss how we think you could do this. Imagine the binary is quite compact to begin with, right? So you have these two stars that are massive stars, fairly low metallicity, and they're almost in contact. Or maybe, as Pablo Marchand and collaborators have pointed out, actually in contact. They're already having a bit of Roche lobe overflow even on the main sequence. So now it's a very close binary, and tidal forces are going to be very strong because it's almost Roche lobe overflowing. So tidal forces are so strong that you force the stars to be tidally locked and therefore to be quite rapidly spinning at something like 30 or 40% of their breakup velocity. The combination of this rapid spin and the strong tidal forces enhances the mixing within a star. You have circulation enhanced by this rotation, rapid rotation, and as a result, instead of this standard picture where, as I said, you have this helium-rich core and a hydrogen-rich envelope, and eventual expansion, you've got this material which is helium-rich throughout, and it just collapses or shrinks into a helium star and ultimately in situ into a black hole. You never have mass transfer, except a little bit that's lost through winds, of course. You never have this common envelope. In a way, it's a much simpler picture. Now, okay, there are big questions whether or not this really happens and exactly when it happens. What are the requirements on the mass, the metallicity, the rotation rate in order to give yourself chemically homogeneous evolution? There's also some debate about whether chemically homogeneously evolving stars have actually been observed or not. Some indication that maybe they have. Some nearly contact, rapidly rotating, almost kissing binaries have been observed. But at least it's a possibility. And so if that happens, and there's only a fairly small window for this, right? You need a pretty high mass because you need your star to be, to a large extent, radiatively supported. You need quite a rapid rotation. And of course, you don't want the stars to actually be in contact because, okay, you can have a bit of Roche-Loeb overflow, but you don't, you cannot let them be too close, otherwise they just merge too early on. So there's sort of this little sliver of parameter space where the initial orbital periods have to be on the order of a day or two, and the initial masses probably have to be 40 solar masses or above, where you can actually have this chemically homogeneous evolution happening. But in that case, you do get merging black hole binaries, at least in our simulations and in the Marchant et al. Simulations. One interesting thing is that they could give you very different time delay distributions between formation and merger, because the common envelope can actually very significantly harden the binary. So that at the end of the common envelope, you almost end up with a binary that's sort of, where the two black holes are, in some cases, going to merge in less than 1 million years after the common envelope phase, after the two black holes are actually formed. Here, you don't have this. So essentially, your binary kind of stays the same separation it was at initially, which means that you have a much more of a flat distribution in terms of the time delay between formation and merger, going from a few billion years to about 10 billion years, so within a Hubble time. But the point is that none of these very short time delays, so that could be possibly a distinguishing signature of the scenario. Of course, we checked whether or not there is a reasonable probability of detecting these things, and the answer is yes. You do, in fact, expect to detect a few of them roughly the right rate, even at the sensitivity that LIGO had during the 01 surge. You may be detecting sort of order of 1 a day by the time that LIGO reaches the design sensitivity. The mass distribution is basically just right for GW 150914. It's not right for the lower mass LIGO observations. This channel is probably not consistent with GW 151226, for example. But nonetheless, it's an interesting possibility, another way of forming these binaries. Okay, and what about letting the stars evolve before they make a binary? This is a typo. It should say dynamical formation in clusters. So you take a dense stellar environment, put a bunch of stars there, let them evolve into black holes, not necessarily in binaries with each other. They might be in binaries with something else. They might be just sitting there on their own. Doesn't matter. You now have a whole bunch of stellar mass black holes flying around, and sometimes they will interact. They can interact in different ways. They can interact by gradually, by forming first binaries and then gradually hardening through many 3-body and 4-body interactions. They can possibly, in some situations, have direct captures through a single burst of radiation emitted at a flyby. They maybe, in some cases, are helped along by the presence of, let's say, a disk, if this is happening in the galactic nucleus. So there have been discussions of these, including several of the people here, of course, who have contributed very prominently to this, about how this might happen in stellar clusters and globular clusters, how this might happen in galactic nuclear clusters. I'm going to show one plot by a gentleman who I think is standing in the back of the room, if I can see right from here. So this is work by Carl Rodriguez from MIT. There's Carl. Wave Carl. So I'm not involved in this work, but I'm nonetheless sort of quite proud of the work, because when Carl was starting his PhD, I was his co-supervisor, and a second Carl Haster, second Carl in this paper was until he graduated a couple of months ago, was my PhD student. And so in this example, here is a beautiful diagram of again how you might form an event like GW150914, either through, as you can see, a very long series of interactions where at some point you actually have the final interaction as an exchange interaction where one of the companions, being a more massive object than whatever is already there in the binary, comes along and substitutes itself in during 1 to 3 body interactions, or gradual scattering interactions with occasional flybys that take away a bit more energy than they bring in. In both of these scenarios, you ultimately form a binary which actually is likely to merge outside of the cluster because it was probably kicked out of the cluster during the last strong interaction, and give rise to an event like GW150914. Okay, what's a dinosaur doing here? Maybe I'm in the wrong audience. I meant to give this talk to paleontologists, sorry. Okay, I'm not quite that confused, although I am severely jet-lagged, as you can probably notice by now. But now I wanted to say a few words about a project that we've been ramping up in my group over the past year. We're calling it COMPASS, Compact Object Mergers, Population, Astrophysics, and Statistics. And our idea is to try to solve the inverse problem, right? I've told you a little bit about the formation scenarios. I think you can probably guess that in many of these scenarios there are lots of uncertainties, lots of free parameters. Do we know exactly what kinds of kicks black holes get during their supernova? What are the natal kicks? Do we know exactly what happens during the common envelope phase? Exactly what the efficiency of transferring orbital energy to the ejection of the common envelope is? Do we know, for example, in the chemically homogeneous evolution, exactly what is the parameter space in which the stars are able to evolve chemically homogeneously? So there are lots of these questions, and some of these questions, of course, relate directly to our understanding of some very basic physics, such as the physics of supernova. And so it would be really nice to be able to constrain these. And our goal is to try to use a population of observed sources to now solve the inverse problem and figure out what they tell us about binary evolution. And the reason I put on a picture of a dinosaur is that it's a little bit like paleontology in the sense that you can think of these LIGO observations as remnants of massive stars. They're kind of like dinosaur skeletons, right? And a good paleontologist can, pick up a little bone here, thigh bone, skull bone, whatever, and look at it and say, I know that this was a herbivore, this was a carnivore, I know how it walked, I know what it ate. We'd like to do something similar. We'd like to look at these black holes, these remnants of massive stars, and say, okay, can we figure out how the stars evolved given these observations of their remnants? And of course, we cannot do it for any one system, but if we have a whole population of these, the answer is, well, actually, maybe we can. So how do we go about doing this? Let me mention that the 3 people who are leading this work are my students, Alejandro Viña-Gomez, Simon Stevenson, and Jim Barrett, and we have lots of collaborators, and we're always looking for more. So if you're interested, come talk to me. But okay, remember, for example, this picture of the uncertainties in the measured LIGO events. Now, we decided to ask the following question as the first question. Okay, let's suppose we know that there are some problems, for example, reproducing these events with the lower mass events, for example, with the chemically homogeneous evolution channel. So let's ask the following question. Can we at least robustly reproduce all 3 events through the same channel without having to separately tweak our assumptions and say that, well, to get this event we have to assume one thing about black hole kicks, but to get this event we have to assume a different thing about black hole kicks, and so on. So we try to make some reasonable assumptions about the evolution of the binary? And the answer turns out to be yes, we can. So we evolved the population of sources, in this case at 0.1 solar metallicity, and highlighted, of course, we have an overall population. It's not that there are gaps here somehow magically, but we highlighted in color those sources which would have appeared to be similar to one of the LIGO detections. And as you can see, we've got indeed sources for each of the LIGO detections in the LIGO candidate event. So yes, the answer is we can robustly reproduce these. By the way, just to show you, here is, for example, the evolutionary history of one of the systems, one of these orange systems over here that forms something that looks like GW151226. It's again one of these Ed van den Heuvel style diagrams. Here, of course, you end up with a 7 and a 14 solar mass black hole, starting with roughly 50 solar mass progenitors, but now at solar metallicity, so much stronger winds. We can reproduce events like this at solar metallicity, not GW150914, that requires us to go to something like 5% solar metallicity. Okay, in the interest of time, let me move on and bring up the following point, which is sort of one of our next challenges. Okay, for one particular set of assumptions, yes, we can reproduce these events. Good. But at some point, once we have more observations, once we have a whole population of sources, we want to test whether these assumptions are right. We want to test, well, do we believe our default value for the black hole kick distribution? Do we believe our default value for the common envelope efficiency? And so on and so forth. Now, of course, people have tried to do this before, but the way that people have typically done this is that they said, okay, well, here is, our schematic of a binary evolution. By a question mark, I have denoted each one of my uncertain parameters. So the initial mass distribution, the initial separation, and the distribution of that initial separation, the efficiency of mass transfer, the wind strength, the supernova kicks, the common envelope physics. That's mostly question marks. It's very uncertain. In fact, the one thing that has no question marks is the final part, which is the gravitational-wave emission. That one we actually think we understand pretty well. Everything about astrophysics is very messy. I'm still new to learning about this astrophysics business, right? I was trained as a classical general relativist, so this is the one thing that I feel comfortable about. This sort of raises heckles still. But we have all these question marks, and sort of each question mark you can think of as corresponding to an assumption or a parameter that we could in principle vary. And the question is, okay, can we actually constrain them? So one approach to this has been the following. So this is actually, again, work that my student Simon Stevenson had led. Let's take a few different models. So these are models from a paper led by Michal Dominik, one of Chris Blaczynski's students. So this is a paper we had written with them a few years ago. By the way, this paper did actually predict that, as you can see from here, that it's perfectly reasonable to have chirp masses extending up to 30 or 40 solar masses in many of these models. So it's not that this is completely unexpected that LIGO has seen this event, but and there have been, of course, other people who have predicted similar things. But here there are a few different models, and what we did in that paper was we said, okay, let's vary one parameter at a time. Let's take sort of our standard model called S, and then I don't even remember right now what these various numbers correspond to, what each model was, but in this model, let's say we change the black hole kick velocity distribution. In this model, we change the common envelope efficiency. And in this model, we change the luminous blue variable winds. And in this model, we change the Wolf-Rayet winds, and so on. And we sort of move one parameter at a time. And then what Simon had shown was that, in fact, if you assume that the data comes from one model, you can ask the question, well, can I figure out, given a data set of a few tens of observations, which model the data really came from, right? So the way to read this is forget about the four square, just focus on, let's say, the top left square. So this says, okay, if the data really came from model 11, how confident am I that it's really model 11 that is the right one, right? So here, for example, it says, okay, if model 11 is very different from all the other models, so if the data really comes from model 11, I'm sure it's model 11. Here it says, oh, models 5, 6, and 7 are pretty similar, so the data comes from one of those models. I can't really tell whether it's more consistent with model 5 or model 7 because they give you roughly the same merger rates and roughly the same mass distributions and so on. Okay, so that's the first step. But these are really changing one parameter at a time in this multidimensional space, and we know there must be correlations between these parameters, right? So it's not quite the right answer. If I tell you that I ruled out it's definitely model 11, you shouldn't believe me, because it may be that actually if I go for model 0 and both vary the supernova kicks in one direction and the common envelope efficiency in another direction, I would actually get back to the same prediction as I would get in model 11, where I actually varied some other parameter, let's say the mass loss rate. So that's a fundamental problem. So now we somehow have to populate this very large dimensional parameter space, and that becomes very computationally expensive. So that means we've got to start interpolating. So this is one of the things we've been working on, work led by my student Jim Barrett, trying to figure out how to actually build tools for interpolating in a large dimensional, let's say 10-dimensional parameter space of models where I only generate something like 100 models. Now each model I'm generating as a as a Monte Carlo, it's a population synthesis model. So I take at 100 different points scattered around this parameter space, I take 1 million binaries, evolve them forward, figure out what the merger rates are, figure out what the mass distributions are, and then I do this at 100 different points, and now I want to have a prediction everywhere in this model space. So I have to interpolate. So this is something that Jim has been working on, and he's been finding some success, for example, in terms of interpolating the merger rates as a function of these parameters. By the way, one of the other things that's coming out of this is also an ability to figure out exactly what the real degeneracies are between the parameters. That's something we don't actually know at the moment. What are the combinations of parameters where you could move one parameter this way, one parameter this way, and you end up with something very similar in terms of model prescription. We know this must happen. We don't know what those degeneracies are, so we're actually learning that right now. And then ultimately, the goal is to reconstruct the binaries, but I'm actually going to, let me actually skip some of these slides because we're running out of time. And I think I should probably end it here to make sure that people have a chance to ask questions. So what's the ultimate goal? Well, the ultimate goal is to bring together the modeling of binary populations with astrostatistics to figure out what are the questions we really can hope to answer, because there will be some degeneracies, there will be some uncertainties, and then to start answering them with the data available, and to also start using the full observational data set, not just LIGO observations, those are great, but that's not going to be enough. There will definitely be degeneracies between these evolutionary parameters if you're only looking at the dinosaur skeletons, if you're only looking at the compact remnants. We have to take all of the available information that relates to the evolution of massive binaries, X-ray binaries and dual X's, the galactic population of binary pulsars, luminous red nova if we think they are associated with common envelope events, gamma ray bursts, supernova. Take all of that into account, and each one of those populations will have some degeneracies, but hopefully the degeneracies are different, and we can build something like the equivalent of a concordance cosmology, a sort of concordance picture of binary evolution. So that's the goal. It'll take some effort, so wish us luck, and thank you. Oh, okay. Ariel?
So I actually have two questions. One is about, you described that this is a very multidimensional parameter space, but you showed us a particular example of 250 solar mass irregular sequence stars ending up as one of your sources. So I understand it's very multidimensional and there will be the degeneracies between different parameters, but how finely tuned did those masses have to? Just looking at the mass ratios and initial masses. How finely tuned do they need to be to get you there?
So when I was referring to the sort of the uncertainties, I'm going to find the right picture in a moment, I hope. Okay, yeah, yeah, I'll get to this one in a second. But I was actually mostly referring to the parameters governing the binary evolution rather than the parameters of individual systems. So I'm sort of mentally separating those, right? So the mass I'm thinking of parameters of individual systems. In the end, I don't actually care as much about the parameters of the individual systems. I mean, whether this particular system came from a 40 plus 40 solar mass binary or 50 plus 50 solar mass binary interests me a lot less than the question of what is the typical supernova kick that black holes get when they're born, right? So it's sort of the hyperparameters, if you wish, that I care about. But in this case, for this particular set of hyperparameters, right? So we fix the physics, if you wish. We fix the distributions from which we draw supernova kicks. We fix the efficiency of the common envelope projection. We fix the luminous blue variable winds and so on. And now we just ask, okay, what are the progenitors of these systems over here, the systems that make binary black holes that could look like GW151226? The answer is, all of these systems in orange could have formed that binary. So that means the initial masses, and this is, by the way, I should say, this is at 5% solar metallicity. So the initial masses could be, on the order of 35 plus 35 solar masses, but could be, for example, 25 and 60 solar masses. There's also a third parameter I'm not plotting on here, which is the initial separation, which of course also has a strong effect. And the metallicity has a strong effect because, for example, if you compare this plot over here to this plot over here, let's look at the greens. So the greens are the LVT progenitors, right? You see that at 5% solar metallicity, it's kind of the typical progenitor is something like 50 plus 50 solar masses. But at solar metallicity, the typical progenitor for the same event is 80 plus 80 solar masses, right? So why? Well, because you have much more mass loss at higher metallicity, and so you need to initially have that extra reservoir of mass, which is also why on this plot you don't see any blue dots, any progenitors of the most massive LIGO event, GW150914, because we're actually not able to form it at solar metallicity.
Yeah, so even though you don't consider one of your hyperparameters, I was mostly interested in how finely tuned the mass ratio needed to be. The answer seems to be not very finely tuned.
No, the mass ratio doesn't need to be very finely tuned, but one very interesting question is how finely tuned does the mass ratio of the merger product end up being? And this is actually interesting. If you look at this plot over here, you will see that the mass ratio has a much greater extent at lower metallicity than at solar metallicity. In fact, at solar metallicity, we are finding it's very difficult to, whatever, you may start with quite unequal binaries, right? Some of these binaries, look at this one. This one has, initial masses of 85 and 35 solar masses. And it ends up essentially as an equal mass system. So we think we understand why. It's basically because of the multiple episodes of mass transfer that happen between the stars. They actually tend to equilibrate the mass of the system. But that's not the case at lower metallicities. And so that means if you can measure a system where at the time the binary merges as a black hole binary, the mass ratio is definitely unequal. Let's say you measure something that has a 3-to-1 mass ratio. It's pretty clear that it could not have formed, or is very unlikely to have formed, at solar metallicity through this channel. Now, previously people have actually argued that that could be a strong indication of a dynamic of formation channel, because people actually were looking at plots like this and were saying, plots like this produced with other population synthesis codes, and saying, look, you cannot form unequal mass binaries through isolated binary evolution. That's not true. The statement is you cannot form or unequal mass binaries for isolated binary evolution at solar metallicity. So a very unequal mass ratio could be a signature of dynamical formation, or it could be a signature of this isolated binary evolution, but at lower metallicity. Yes, please.
Does all of this argue in favor of LISA versus LIGO, the space-based gravitational wave, insofar as it, as I understand it, is able to study systems not in the last second of their existence, but much earlier, and therefore gives one an opportunity to study the system and its environment before the ultimate collapse?
So I think it's not an either or, I think it's an and. So we definitely want both LIGO and LISA. There's no question that LISA can do fantastic science, and we desperately hope that LISA will indeed fly. Well, supposed to fly in 2034, maybe even a few years earlier, now that people are excited about LIGO results as well as the success of the LISA Pathfinder mission. So you're absolutely right. There are some things that LISA will be able to tell us even about stellar mass binaries, although LIGO is still probably the machine of choice for stellar mass binaries, and there are some things that LIGO will be able to do much better. For example, LISA has no hope of, let's say, probing the equation of state of binary neutron stars simply because it's looking at things at a much lower frequency band where there is no sort of genuine interaction between the neutron stars, whereas, for example, if you are observing a black hole neutron star binary that's at the moment of merger, you can see by checking, okay, when does my signal end? Essentially, it ends at the moment of tidal disruption of the neutron star. That tells you how stiff the equation of state of the neutron star must have been, for example, right? So there will be something that LIGO is really much better for, but I completely agree with you that LISA will give us complementary information. It'll be very exciting. Warren?
Just a question, comment that binary evolution often bifurcates, whether you have a common envelope or not. So how do you count that in your interpolation?
So we're not trying to interpolate individual systems, right? We're trying to interpolate distributions. And so we are beginning with a broad distribution over the initial properties of the system, right? That's why we're sort of evolving forward, 1 million or 10 million systems. We end up with a rate and a mass distribution, let's say a Church mass distribution at the time of merger, and then we interpolate those distributions. So those distributions, of course, take into account this bifurcation, if you wish, but the bifurcation basically, if you wish, is a probabilistic statement. We're interpolating a probability distribution already, so that's automatically handled by this approach.
Can I, maybe you alluded to it in earlier part, but how well do we know the spins of the, before the merger of the each of the component black holes?
So that's a very good question. The answer is not as well as we would like. So we know the things we definitely know are, one, we did not have rapid and aligned spins, aligned with orbital angular momentum, so that is ruled out. We can also rule out for at least one event 2 non-spinning black holes. For the last event, GW15 1226, it cannot have been that both black holes had a spin of exactly 0. In between, most things are possible because it's very difficult in a few cycles to measure the precession that you would need to constrain well the spin components in the orbital plane. So that's our biggest problem. We can at least put some constraints on the spins along the orbital angular momentum, but not the spins in the orbital plane. But that in part depends on just the configuration. So for example, if we were more lucky, if we detected a binary that was edge-on as opposed to face-on, if you have a face-on binary, precession does this, not much of an effect. If you have an edge-on binary, precession does this, big effect, right? So if you're lucky enough to detect an edge-on binary, for example, then you can get much more information about precession. So we just have to wait and see. Sorry. Go ahead, Joe.
So this common envelope bug is, really nasty. What do you think we're going to do about it? Because people have been worrying about this for decades, and the progress seems to be painfully slow, and yet it's central in at least, multiple stages in these Van den Heuvel type diagrams you were showing, not just even at the beginning stages when the first guys, the more massive, the accretion is unstable, so you're always, dealing with this.
So
yet you're modeling it like everybody is, as far as I know, with just one efficiency number, which is just our statement of we don't know what's going on.
Exactly. That number is certainly not a universal parameter. There's no reason to expect it to be a universal parameter.
Yeah.
So I think that the thing we would like to do, of course, the right thing to do would be to have a good physical model, and one of our collaborators, Natasha Ivanova, for example, who is very actively working on this. But as you say, it's a difficult problem, progress is slow. So our approach is, okay, if we don't know what the answer is, let's see if we can at least consider a variety of alternatives that hopefully bracket the truth and ask, are there truly robust predictions, right? Because, okay, to be honest, this you actually shouldn't get too excited by, right? Because the fact that, okay, like we've seen some event, and I give myself a big box with lots and lots of knobs, and I tune enough of those knobs, and I say, look, I can reproduce the LIGO event. Okay, great. If you give yourself, if I give me 20 more knobs, I could reproduce it even better, right? What you should be excited by, though, is the following. If I tell you, no matter what positions I put these knobs in, there is some robust prediction that I make no matter what. For example, one of the things that maybe is fairly robust, we're checking it at the moment, is the time delay distribution, right? Time delay distribution, is it uniform in the log of the time delay between information and merger? If, for example, that's a robust distribution, that's something you can test, because we know what the star formation rate is. We know how you can involve it with a given time delay distribution model. We know what the merger rate is as a function of redshift. Let's go out and measure it. LIGO will do that. Now, okay, it'll take more than 3 detections, but eventually we will do that. Now compare it. Now, if I tell you, no matter where I put the knobs, it's always a flat in the log time delay distribution, and the observations don't match that, okay, now you know that fundamentally I missed something in my model. Now I go back and we've learned something, right? By saying that I've missed something, we've actually learned that fundamentally either this is the wrong model, binaries don't actually form, binary black holes don't form this way, or there is some key physics that I missed in this description, right? So that's, for example, one of the approaches we're trying to do. So we're trying to consider what is the broadest set of reasonable, plausible assumptions we can make, and what are the robust predictions we can get out. Avi? Sorry.
So there is another aspect of metallicity which you didn't mention. Aside from the winds being weaker, the mass function of stars will be quite different with low metallicities, and enhancing the high mass star abundance. And given these time delays that you get quite long, then you would be sensitive to the question of what the mass function of stars is at high redshifts. And the question is how to disentangle that. So perhaps analysis of the time delay distribution that you just mentioned could say something that it could be quite a large effect, because the abundance of massive stars is small usually, but perhaps at low metallicities they really are much more prominent.
Indeed. No, I absolutely agree with that. And in fact, it's even as it is, even if you assume a universal IMF, we found in Dominic et al. 2015, for example, that, and I think I mentioned this when we were chatting earlier, that actually most of the black hole binaries that are emerging today locally at redshift 0 were formed in the first billion years of the life of the universe, despite the fact that low time delays are disfavored by this uniform log distribution, because the metallicities were so much lower there, and so low metallicities are conducive not just because of low mass loss rates, but also because of the way that the radial expansion happens. You want the star to expand at a particular time during its evolution in order to survive the common envelope and so on. And so when the expansion happens is key, and metallicity determines that as well. So for all of these reasons, it's low metallicity environments are preferred. If the IMF is top heavy at low metallicity, that would make it even more preferable. Absolutely.
Okay, let's do one more question.
I actually had a question about this alternatives, because there was a Nature paper, I think it was by Belczynski a couple of months ago, where they claimed that they have solved the system. What do you think about it? Because they managed to get away without a supernova. They say that it's a direct collapse.
So okay, so the plot that I'm showing you here is actually very similar to the plot in the Belczynski paper. I mean, this is our code versus their code, but it's in fact the codes are fundamentally similar. We make slightly different assumptions about mass transfer efficiency and so on. I mean, by getting away without a supernova, they just mean that you have to make some assumption about what is your model for what happens if you have a 40 solar mass star that is done with its evolution, right? Is going to is it going to have a failed supernova and basically have a nearly complete collapse, or are you going to eject a non-negligible fraction of material? And in that model, the assumption is that you have a complete or nearly complete collapse for sufficiently massive progenitor cores. Consider that one of the additional uncertainties, although unless you want to argue that your yes, consider it one of the extra knobs, although I think probably that knob isn't too important, because typically, unless you imagine that somehow a 40 solar mass star is going to collapse and give you a 3 solar mass black hole, that seems a bit unlikely and implausible. But unless it's something extreme like that, even if you assume you have a few solar masses lost during a supernova, the biggest thing that could lead to is a kick. But the kick actually isn't all that important, because typically you have already quite tight binaries here. If you want to merge in Hubble time, you need them to be quite tight. And these are massive stars, so if they're massive and tight, it means you actually have a pretty high orbital velocity. So the typical supernova kick, even if you give these things kicks of order of the typical neutron star kick of a couple of 100 kilometers per second, is likely to be lower than the orbital velocity by factors of a few, meaning it's not going to change your binaries orbital parameters all that much. So it's actually not likely to make all that much of a difference.
Okay, let's thank Ilya again.
Thank you.